Hello, students. It's Mr. Rich. It's Sunday, November 10th. We're doing another Mr. Rich Q&A. If you've got questions for me, send them to askmrrich@gmail.com. I did get a question from Avery, and I am going to try to pull this up, and we'll take a look at it. Looks like it comes from Delta Math. And Avery, I guess this would be Algebra 2, I guess is what this is. But let's take a look. I am going to go over towards the end, or if we have a lull in this, I am going to discuss what in the world logarithms are, because a lot of you that are in AP Calc are about to study logarithms. And those of you that are in AP Calc could probably use a refresher on logarithms. All right. So again, askmr@gmail.com. You can take a screenshot or a photo of any homework problems that you want me to work on, and I'd be happy to give a shot. Give it a shot. So let's look at this. I will share my screen and see what we got. And there's the chat. This is it. This says -3 g inverse of f of 13 plus g inverse of -14. Well, one of the things that you need to do if you're reading values off of a table for a function is if you're finding inverse values, then you read the table backwards. That's the whole secret here. Well, I'm going to start in the innermost part of this, right? So if I'm evaluating this, I want to follow, just like we taught you in order of operations, we kind of start at the innermost part of the parentheses. So I'm going to start at f of 13. F of 13 means find x equals 13, because that value right there is an x value for the f function. So we find where x is 13 and we read the y value under the f of x column. So that's 15. So this is -3 g inverse of 15. So I just replaced f of 13 with what it's equal to, which is 15. So this means here g inverse of 15. Let's write that a little neater there. G inverse of 15 plus, then there's a g inverse of -14. So I am now going to read the table backwards, right? Because here's why. Yeah, this still represents an x for the inverse of g function, which means that it is a y value for the g of x, which is the inverse of the inverse. So that means then if I have a table of g's and not a table of inverse of g's, I need to be looking in the y column for -14. So I'm reading the table backwards. Here's a -14, and it is associated with the x value of -3. So just for clarity, I am going to write what I just discovered here. That must be equal to -3. And you may say, well, how? Well, here's why. Because wouldn't you agree with me that from this table, g of -3 is -14. That's how we normally read a table of x's and g of x's. That's an x value, that's the y value. So this tells me, just being even more precise here, what this tells me is that the point -3, -14 is on the g function. And that makes sense because the inverse function is just where we've swapped all the x and y's. So this would be on the inverse function, it must contain the point -14, -3. Okay, all of that to say that I'm just trying to explain in more detail why this is inverse g of -14 is equal to -3. So this is plus a -3. Now we have to finish the problem. This is g inverse of 15. So I'm going to read the g backwards. I'm going to find 15 in the g of x column and read the associated x value. It is 7. So inverse g of 15 is 7. So this is -3 times 7 plus a -3, which is the same as -3. So my answer here, Avery, I would call this -24. -21 minus 3. And if I'm wrong, I apologize, but no, I think that's right. But I think that would be the right answer. You can see if Delta Math likes that answer or not. All right, if you have any questions about that, let me know. I see if another problem coming through. It's a calculus problem. And this is the problem. All right, this is from Taylor. This says a tube is being stretched while maintaining its cylindrical shape. The height is increasing at the rate of 2 millimeters per second. At the instant the radius of the tube is 6 millimeters, the volume is increasing at the rate of 96 pi cubic millimeters per second. Which following statements about the surface area of the tube is true at that instant? The volume V of a cylinder with radius R is that, and the surface area of a cylinder, not including the top and bottom, is S equals 2 pi R H. So all of these answers are asking us to find the rate at which the surface area is increasing. So they're wanting me to find what we call ds dt right there. That's what they're asking us to find. And let's go through this problem. So if you're a calculus student and you're in unit 4.
Right. Actually, I do know how to solve this problem, and I'm going to work it now and splice this into our Mr. Rich Q&A for Sunday, November 10th. What I'm going to do here is in this problem, I am going to take the derivative of the volume function here with respect to time on both sides. So when I do that, I will use the product rule. And when I was working this problem last night, that's indeed what I did. Because I didn't have any relationship between R and H, so I did have to take the derivative as it is. So I'm using the product rule because I've got pi r squared times h, two different variables. So I take the derivative of the first, which would be 2 pi r dr dt, times the second, which the second function is h, plus the first pi r squared times the derivative of the second, which is just dh dt. Now what I'm going to do is I'm going to plug in the quantities that we were given that would fit into this formula. We were given the rate of change of the volume, and we are told that at the moment that the radius is 6 millimeters, that dv dt is 96 pi. So we put in 96 pi here. We're going to put in 6 millimeters for the radius. We don't know the rate at which the radius is changing, nor do we know the instantaneous height at this moment when the radius is 6. So we're just going to put dr dt h. Here, this term, we can put in a 6 millimeters for the radius. I'll rewrite this like that. Now, I did forget up here to put in the 2 for dh dt because they did tell us that the height is increasing at 2 millimeters per second. So the dh dt is actually 2. So this ends up being 72 pi. When I subtract 72 pi from both sides, that makes this 24 pi equals 12 pi dr dt times h. Dividing both sides by 12 pi, here's what I get. I get this relationship. I get the fact that dr dt times the height is going to be equal to the number 2. This then allows me to take the derivative of the surface area, and I'm going to be able to use that result in that derivative. Let's write down the formula for the surface area that we're talking about. So this is the surface area of a cylinder without a top and a bottom. This is 2 pi r h right there. And we're going to take the derivative. And we do have to take the derivative also using the product rule because I have a 2 pi r and an h. Those are my two functions that are being multiplied together. So when I take the derivative with respect to time, it's going to look like this. Okay, and so that is what I get after taking that derivative. Now, what we can see here is this is what happens. I'm going to use this result that dr dt times h is 2. So I'm going to replace this quantity right here with 2. That's going to make this 4 pi. Over here, we know that we're talking about at the instant that the radius is 6. So we can plug in 6 for r. And we also know that the height was, go back up here, the height was increasing at 2 millimeters per second. So this is going to be replaced with a 2. And we're almost there because now this becomes 4 pi plus 24 pi. 6 times 2 times 2, 24 pi. So our result is that the surface area is increasing at 28 pi square millimeters per second. And that is our answer A. Okay, I hope that helps, class. Like I said, I'll give you this one comment. I always preach to my students that when you don't see a pathway, sometimes you just have to do what you can do and see what happens. And in this instance, the do what you can do was to take the derivative of both the dvdt and the ds, or find dvdt, find dsdt. And then what I should have done, excuse me, my mistake was I should have just gone with it. I should have said, let me see what happens to this dvdt formula when I plug everything in that I was given, right? And I was given the dHdt and I was given the R. I was not given these two quantities. But if I had gone all the way with this, I would have come up with this relationship. And then hopefully at that point, I would have seen that I could have made a substitution into the result of the derivative of the surface area. Okay, that's going to be it. Thanks.
Equation. Well, cosine is adjacent over hypotenuse. In this picture that I have here, there's my adjacent side. The hypotenuse is going to be the square root of h squared plus x squared by using the Pythagorean theorem. So that means then that I can really write cosine theta as x over the square root of h squared plus x squared. Now, what I want to replace is not just cosine theta, but cosine squared. So I'm going to actually, before I substitute it, I'm going to get cosine squared. That would be x squared over h squared plus x squared when I square that fraction. So now I think I'm really close to getting the answer that I want here, because I'm going to say d theta dt is negative h over x squared times x squared over h squared plus x squared. Looks like those x squareds are going to cancel. It should leave me, and yeah, h squared plus x squared. All right, let's look at those answer choices. Yeah. Oh, and by the way, one of the things that, yeah, where did my dxdt? Yeah, notice, my goodness, up here, when I took the derivative over here, I needed a dxdt out here by the chain rule, right? Because I was taking the derivative with respect to time. So as soon as I used the power rule here, I had to have a dxdt. So all along here is a dxdt. So yeah, coming down here as a last part of my answer, there is a dxdt right here. So it looks like here, Taylor, A is going to be the answer. That's going to match up right there. Okay. Not the easiest of problems for sure when it comes to those, but hopefully that helps. All right. I see another one coming through. Edson sent one. Let's do it. I'm pulling it up here, Edson. Let's see if we can take a look. All right. Looks like a delta math problem. Let's slap it right there. And tell me if that looks right, Taylor. I think that was right. But anyways, a delta math. Here we go. Okay, we need to find the inverse function. So if I need to find an inverse function, so this must be an AP, this got to be an AP pre-calc. Edson, are you AP pre-calc? Yeah, I thought, yeah, because I think you're on that Tuesday call. But yeah, so this is we're doing in AP pre-calc, we're doing inverse functions and composition functions. To find an inverse function, we do need to swap the x and y variables. That's really our starting point. So this is going to be x is equal to the 7th root of y plus 1 over 9 minus 3. So I just have to do the algebra steps to solve this for y, and then I have found the inverse function. Well, the first step, I'm going to have to add the 3 over, right? So I'm just following what I know in basic algebra to solve this for y. So it leaves me with this. The next thing I got to do is get rid of the 7th root. So I'm going to raise to the 7th power on both sides. So that's going to give me x plus 3 to the 7th power. And when I raise that right side to the 7th power, it's going to negate the 7th root and leave me y plus 1 over 9. So then what I'm going to do is multiply both sides by 9. It's going to take me to this spot and then subtract 1, right? And I'm about to look at those answers and sure hope that that's going to be the form that they have it in. And then I would change that y to an F inverse, right? So if you're doing an AP pre-calc test or summative and you're It's a free response question, trying to find the inverse. Make sure as your last step that you change the y that you solved for, change it to the inverse function notation. That might be worth a point. Yeah, so I look at what's here, and I think, Edson, the one that I really like is that one. And my philosophy on this, right, on a multiple choice problem like this, is to look at the next closest answer to mine that I think is right, and then try to justify that that's not the right answer. Yeah, they included the 9 to be raised to a power, and that wouldn't make any sense because I can't deal with the 9 until first I've raised that to the 7th power. So it makes no sense that the 9 would be included in that power of 7. So yeah, I definitely don't like that, and I really love that answer right there. You're welcome, Edson, and you're welcome, Taylor. I don't see any other questions coming through, students. Are you going to force me to go do logarithms? I think you are. Let me go grab the stuff that I need. While I'm pulling this up on logs, then if you've got some questions, send them like Edson did in the chat, or send them to askmrrich@gmail.com. And the material that I'm going to use for this discussion about logarithms, it does come from the AP Precalc in Unit 2. So it's kind of an introduction to like, what are logarithms? And I find while I'm pulling this up, just to tell you why I thought about covering this, is that logarithms are the one thing that I find students just, they never get their minds around what they are or why they exist or how you would ever use them. And they're just like an annoyance, right? Like, it's like, my goodness, why do I have to deal with LOG? What is LOG? Where did LOG come from? All right. So here's my discussion. My goal here is to help you take a different look at logarithms. Okay. I want to start off by really explaining something that you were supposed to pick up in Algebra 2 with regard to what is a logarithm. If I present to you an equation, log 3 of 81. In fact, let's do this. Let's forget an equation. Let's not even get to the point where it's an equation. I just show you that. And you're like, log, LOG? I don't even know what you're asking. What does that mean? I don't know how to evaluate that. Well, I want to show you something that maybe is an analogy to it in mathematics that might make some sense. When I ask you for the square root of 25, you all know that that's 5. And you can say plus or minus 5. Okay. But let's just use a positive value here, 5. Right? That is asking the question, what number, when raised to the 2nd power, gives you 25? You actually have to ask that question, right? Because it's an implied question in the 25. If I say, what's the square root of 25? You have to think, what number is it when raised to? Because basically I'm saying that there's an unknown. I'm asking what is this question mark? So you have to think, okay, question mark, if I raised it to the 2nd power, what would give me 25, right? It's like a variable, right? It's like, say, okay, variable. What number when I raise to the 2nd power is 25? That's what this is asking you. Well, that's sort of kind of what this is asking you. This is asking you 3 raised to what power would give me 81? That's the question that this is asking, or that's the question that you have to answer in order for you to know what log base 3 of 81 is. And hopefully you can look at that and just know that, well, I think that's 4, and it is, right? This thing is 4. This is the number 4. So that's why this is an equation. This is a true equation because this thing is the number 4. So think about what that is. That is telling you that logarithms and exponentials are inverse functions of each other, because in the same way squares and square roots are inverses. Because if I said square root of 25 is what number, if I squared both sides, it would get rid of the square root, right? And I would have x squared equals 25. But really, I haven't answered the question. It just now lets me see the question in a different form. It's now saying what number to the 2nd power is 25? Oh yeah, must be 5. Okay, so I don't know if here's the thing that you did learn in Algebra 2. One of the things your teacher told you in Algebra 2 was you could take a logarithm equation and convert it to an exponential equation. And they told you to take the base of the logarithm, because all logarithms have bases, move it to the other side. It will become the base of the exponent. The 4 will shrink, become the exponent, and you leave behind the 81. That's what we call converting between a logarithm equation and an exponential. And we can go back and forth between those two forms. But I really don't want you to even think about it in those terms. I want you to think of logarithms and exponentials and as inverse functions of each other. And here's what I mean. I'm going to show you a couple of properties of logarithms that for some reason they just don't, I don't know if they don't get taught or they just don't get emphasized enough. And here are the two rules of logarithms that could change how you view logs. If I take log base a of a to the b power, the answer will be b. Because if there's a match between the base of a logarithm and the base of the exponential inside of a logarithm, this is not a mathematical term here, really. I'm just going to say they cancel each other. Okay. And it leaves you just the exponent. Likewise, if I have an exponential a that's raised to the log base a of b, that answer would also be b, because an exponential base a raised to a log base a, they also cancel each other out and leave you with a b. Now, how does this help us? It helps us a lot, okay? Because there's another way to look at this equation. Let's just suppose that this was log base 3 of x is equal to 4. And I told you to solve that for x. What you could do is say, you know what? I am going to raise 3 power on both sides. That's what we call exponentiate. I'm going to raise 3 power on both sides, so that my equation is now 3 raised to the log base 3 of x equals 3 to the 4. Well, like I told you, that property that I just showed you, these cancel. It leaves me x. Oh, x is 81. I just solved it for x. In other words, I just got rid of the logarithm by exponentiating on both sides of the equation. How do I get rid of logs? Exponentiating. How do I get rid of exponentials? Use a logarithm. Show you what I mean. Let's suppose that this problem, this is a true statement. 125 to the 1/3 is 5. But let's suppose that this was 125 raised to the x power is equal to 5. Well, what I'm going to do is I'm going to take log base 125 on both sides, and I'll take log base 125 of 5. Now, why would I do that? Because these would cancel each other out, and I just solved for x. And x is equal to log base 125 of 5. Now you say, well, I don't know what log base 125 of 5 is. I know. But in technology, using technology, there is a command, math on your TI-84, math log base, where you get to decide what base you're going to use. I'm going to put a 125 in, put a 5 right there, and there's my answer, 0.333, which is 1/3. So x is equal to 1/3. All right, so you can use logs to get rid of exponentials, and you can use exponentials to get rid of logarithms. Okay, let's take a look at this. If they told me to evaluate this, now let's see what the instructions actually are for this problem. It says to find the value of each logarithm. Well, one of the things that I could do, I could use my log base right here and ask my calculator to do it. So I'm going to take math log base. I'm going to take log base 4 of 25, right? And it's an irrational number. It's a decimal number. Now, if this was equal to x, I could exponentiate on both sides. That gives me 25 is equal to 4 to the x power. But that doesn't help me because that just converted it into an exponential. But if I wanted to evaluate this, yeah, I can do log base 4 of 25. And so it's 2.321928. All right, not a great example, but let's move on and I'll show you what we're going to be doing here. Now, this says here to rewrite the following logarithms as exponents. So basically, they want me to convert these to exponential form. So I'm going to think about this as raising 2 power on both sides, exponentiating with a 2. So this becomes 64 equals 2 to the 6th power. Over here, I want to get rid of the log, so I'm going to exponentiate with a 4. I want my base of an exponent to match the base of the logarithm. So I raise 4 power on both sides. This leaves me 1 over 64 because these two will cancel each other out. That's equal to 4 to the negative 3. Yeah, of course it is, because 4 to the negative 3 power is 1 over 4 to the third, which is 1 over 64. What if I want to go the other way? You present to me an exponent and I want to express it as a logarithm. Well, I'm going to use a logarithm whose base will match the base of the exponent. So I'm going to take log base 10 on both sides. See, I'm using logs and exponentials as an algebra operator on either side of the equal sign to suit my purposes. This would leave me, that's to 1,000. So that would leave me, those two cancel. 3 is equal to log base 10 of 1,000. And that is a true statement. And by the way, one of the reasons why I know that this is true is I could rewrite 1,000 as 10 to the third. Guess what log base 10 of 10 to the third is? Well, they would cancel each other out, leaves me an answer of 3. Let's evaluate logarithms without using a calculator. Well, I'm going to use on all of these problems where I'm evaluating this without a calculator, I'm going to use the property of logs that says log base a of a to the b is b. So I want to rewrite the argument of the logarithm with the same base exponential as the base of the logarithm. Well, 625, I believe, is 5 to the fourth. Isn't that right? 5 to the fourth is 625. Yeah. So this is log base 5 of 5 to the fourth. Oh, the answer is 4. So I don't need a calculator there. My calculator could do it, but I can do it without a calculator. You probably remember that logarithms without bases it's an invisible base 10. So this is log base 10. 100,000 is 10 to the 5th power. 1, 2, 3, 4, 5. It's 10 to the 5th power. So that's a 5 because boom, those knock each other out. All right. Okay. This looks like an interesting one. Log 27 to the 80, log base 27 of 81. Well, I want to, wow, so 27. See, 27 is a cube root of 3. So what would 27 to what power would give me 81? I think that's to the 4/3 power because the cube root of 27 is 3. 3 to the 4th is 81. Okay, so you need to, right? If you don't remember how to evaluate fractional exponents, you've got to remember that the denominator is a root, and then the numerator is going to be the exponent that you would apply to the root. So here you take the 3rd root of 27, which is 3, then 3 to the 4th is 81. But now that I see that there's a match here, I purposely made these two guys match up. I know that the answer here is 4/3, like that. If you go and try this on your calculator, go to math, arrow up to log base, and do a base 27 of 81, we'll probably get 1.333, which is 4/3. Okay, let's do a few other things here with logarithms. Yeah. And then what we're introducing to you in section lesson 2.7 is the idea that, as I was just explaining, logs and exponentials are inverses of each other. They undo each other, it says right here. Right. So this says find the inverse of each of the following. Okay, well, let's find the inverse of this log function using what we know about inverses. Right. To find an inverse, I would swap my variables. it would look like this. And then our job is to solve it for y. Well, what I would do is I would divide by 3. Okay, and then I'm going to exponentiate with a 5 power on both sides. So this would be 5 to the x over 3 is equal to y, and that would be the inverse function. So the inverse function of x would be 5 raised to the x over 3, like that. All right, what else can I tell you about logs and exponentials? Let's go to 2.11. Yeah, graphs of logarithms. I don't think I want to go to graphs of logarithms. I think I want to just wrap this up by just showing you just simpler versions of why we like logarithms. Let's suppose that we have an exponential function, and it's some sort of exponential growth function where the initial value is 123 and it's raised to the negative 0.2t. And what we want to know here is we want to solve for t. In other words, we want to find t when a of t is going to be equal to 40. Okay, so what we do is we put 40 in for a of t, and then our job is to solve for t. Well, what I'm going to do is I'm going to divide by 123 on both sides. And then to free up my variable from the exponent, I'm going to use a logarithm. So logs are what I use to free up variables that are in an exponential. So I'm going to use the logarithm that is the same base as the base of the exponential that I'm trying to get rid of, and that's base e, which is also called natural log. So what we do in this case is we take the natural log on both sides, and here I'm going to write it as log base e. That's what natural log is. Log base e of e to the negative 0.2t. Well, these guys cancel each other out. And what we have is the natural log of 40 over 123 equals negative 0.2t. So to solve here, I'm going to do natural log, and I'm going to do 40, natural log of 40 divided by 123, close it off, and then I would be dividing by a negative 0.2. Yeah, so t is equal to 5.617, like that. Let me do one more of those, and we'll do a different base, right? So let's just suppose that, suppose it looks something like this. The amount that I have in an account after I have invested $4,000 is equal to 1 plus 5% over 12 raised to the 12t. So I'm earning 5% compounded monthly. That's what the formula would look like. And I want to know, how long is it going to take for me to double my money? Well, to double my money would mean I get 8,000. So the formula looks like this. Now I'm going to go ahead and I'm going to make this as a base, right? I'm going to do 1 plus 0.05 divided by 12. Okay. So we'll call this 1.004167 raised to the 12t power. Well, I'm going to divide by 4,000, so that gives me 2. And I have 1.004167 raised to the 12t. So I'm going to take a logarithm on both sides. Now, what base logarithm am I going to use? I'm going to use log base 1.004167. That's the log I'm going to use. Okay, so I'm going to take log of 1.004. Now, I'm on my calculator. I'm going to go up and grab that whole thing when I do this log base. But I'm taking log base 1.04167 of 2. But when I take log base 1.004167 of this, it's just going to leave me 12t, because the logarithm base and the base of the exponential will cancel each other out. So basically, divide by 12, and that's going to be how long it would take for me to double my money. So what's that look like on my calculator? Well, I'm going to do this. I'll go ahead and make a fraction. I'm going to call up log base, math, log base. In my, let's see, can I grab that? Let's try to, yeah. So I went up and grabbed that and blew it into the base of that logarithm, and that is 2. And then down here is 12. Okay, it's going to take about 13.89 years. Okay, so logs and exponentials are inverse functions of each other. We will explore that in AP Precalc over the next week or so. I don't see any other questions coming in on the email or in the chat, which means only one thing. I have to go back to Taylor's question, unfortunately, for me, because I'm not sure that I can figure this out in the next 7 minutes. This was the problem we were looking at. So I'm going to take a fresh look here, Taylor, and see if I can. It seems like I've worked this before, but I'm having like a mental block here. So let's see if we can figure it out. Yeah, I needed to get the DSDT, but it's got to be, this is a multiple choice question. It can't be as hard as I'm thinking it is. Well, let me see what, if there's a substitution that maybe I could be doing between these two equations here. Something tells me I can do a substitution maybe. Just don't see it though. DSDT, surface area is increasing. Well, okay, let's talk about whether it's increasing or decreasing. I'm not even sure that we would be able to ascertain that, except the height is increasing, but the radius, if I understand this, the radius has to be decreasing if the height is increasing because they're stretching the tube. So if the height's increasing, the radius is decreasing. Yeah, because the radius is changing, because they say at the instant that the radius is 6 millimeters, the volume is increasing. So, okay, so let's go back here. So if I wanted to calculate, what can I calculate here? We don't know. So we know dHdt. Could I calculate the height at the moment that the radius is 6? That might help. At the moment the radius is 6. No, because I don't know the volume either. I'm gonna have to do some research on this one, Taylor, and get back to you. I'm thinking it's easier than I'm making it out to be, and I'm just missing something on it. Okay, I gave it a try anyways, but I'll figure it out and I'll let you know. Okay, students, what else? What else? Where'd you get this problem at, Taylor? Was this something that your teacher handed out in class? It looks like an older type problem, but is it AP Classroom? Yeah. Okay, I'll figure it out. What else could we do? I know that some of you AP Precalc students are doing some, maybe taking a quiz this week on 2.6 to 2.8. We could do a little bit of work on that. What could I tell you about? Let's talk about 2.8 maybe. Let's do that. So since I think I've got some AP Precalc here, I'm going to pull up 2.8. Spend our last minutes on that. Okay, share my screen. Here we go. These problems here, 2.8 is about finding the inverse of functions. And I want to explain how to find, I'm going to pick this one here and we'll do the inverse function. Now, finding the inverse function is not like the challenge here. The challenge is going to be to find the domain and range of the inverse function. So when I find the inverse function here, I'm going to first swap my x and y variables. So I need to find the function first. So this is going to be x is equal to minus the square root of y minus 1 plus 3. So I'm going to subtract the 3 over first, x minus 3. And then I'm going to, well, we'll just rewrite it like this. I do need to divide both sides by a -1. So that's going to give me negative x plus 3 equals the square root of y minus 1. I'm going to square both sides and then add 1. And that will give me the inverse function. All right. Now, what I want to do is I want to see if I know what the domain and range is of this function right here. Because if I know the domain and range of this function, then I'm going to flip them and it'll become the range and domain of the inverse function. Well, I do know that this function right here, a square root function, it's been shifted to the right 1 and up 3, and it's been flipped, so it's going to open downward. So I really do know what this function looks like. It's going to come over here, over right 1 and up 3, and that's going to be where it would start. And instead of it opening upward like this, it's going to open downward like this. So I know that the domain of my f of x is from 1 to infinity inclusive. So that's going to be the range of this function. This domain is 1 to infinity. The range of this function is negative infinity to 3. So that's going to be the domain here, negative infinity up to and including 3. Now, this inverse function, let's see if this makes any sense at all. This inverse function does have a vertex at, right? So this is a parabola. It's going to have, I'm going to rewrite this as negative x minus 3, the whole thing squared. So it is going to open downward, and it's going to have a vertex at 3, 1. So it's going to come over here at 3, 1, and it's going to open down. Yeah, going to open down like this. Yeah, so its range, so it's over here. Yeah, it's going to be up here at 1 and over here at 3. So its range is going to, see, the domain will be from negative infinity to 3. So we're cutting off basically the right-hand side of this. Negative infinity 3 is the restricted domain. The range is going to be from 1 to infinity. Yeah, you know what? I think that this thing actually would open upward, I think is the way this is going to work, because if I'm squaring both sides of this, yeah, if I'm squaring both sides of that, that does end up being x squared minus 6x plus 9, right? And so it's going to end up being x minus 3 squared. So it's going to be opening upward. And so that means then that, yeah, that would make more sense, because the domain has to be, the range would be from 1 to infinity, because this is going to be, there's still going to be a plus 1 out here, right? Because I had to add that 1 to the other side. So the vertex is at 3, 1, but it's going to open up, and we're only including the left-hand portion of it like that. So my bottom line here is that when you're finding your domain and range of these functions, especially with these radical functions that are converting to quadratics, you're going to have a restricted domain. So you want to find out what your domain and range is of this, and then flip them to become your domain and range down here. All right, students, I think that's going to do it for tonight. I hope tonight was helpful to you, and look forward to seeing some of you next week. All right, everybody, have a wonderful week. See you next time. Thanks for coming.